if x is equal to y, then b to the power of x is equal to b to the power of y. So if we can make the base equal each other, we can conclude that the exponents are equal. In further example, you will see that where it's possible, we would make base, both sides of the equation the same, and from there we conclude the exponents are equal and we solve for unknown. Number 2, if b to the power of x is equal to b to the power of y, if the base is the same, then exponents must be the same. Then x must be equal to y. So we can conclude from b to the power of x is equal to b to the power of y. From there we can say, well, x must be equal to y. Number 3, if x is equal to y and both are positive, x is greater than 0, y is greater than 0, then the log of x must be equal to log of y with the same base. So from here, if I have an equation, it says log of x is equal to log of y, I can just conclude from that x is equal to y. I can just drop these logs and conclude that x must be equal to y and solve for unknown. And number 4, if x is greater than 0 and y is greater than 0, then log of x is equal to log of y. Then from there we can conclude x is equal to y. Notice that the base has to be the same. So let's take a look at some examples. Solve equation involving variable in the exponents. We're going to solve the equation, approximate the solution in 3 decimal places. Here we have 10 to the power of x is equal to 4. 10 to the power of x is equal to 4. If I can make the base the same, I can conclude the exponents are the same, but over here, I can't. So I can take a log of both sides. From here I can say the log of 10 to the power of x must be equal to the log of 4. Okay, from here I'm looking for the exponents x here. Recall that I can move that x right front of log. One property that we learned, have log of x to the power of n. You can write this as n log of x. That's what we're going to use. So in this case, I can take this n and move it right front of the log. Move this n to the right front of the log. That's what we're doing here. We're taking this x here, move it right front of this log. So this becomes x log of 10. We want to isolate x. We're solving for x. So x must be equal to, if I divide both sides of the equation here by log of 10, it would be log of 4 over log of 10. So here I can use my calculator and we can find x is about 0.602. So the solution is 0.602, 602. Solve an exponential equation with base e. We have solve e to the power of 0.02x is equal to 192. Approximate the solution to 3 decimal places. In this case, to solve for x, you have to take a natural log of both sides, ln of both sides. If I do that, I can use the property that I learned. If I have e to the power of 0.02x, if I have natural log of that, I can take this this part here, and I can take this part here and move it right front of this natural log. So this exponents here, from here, I can take it, put it right front of that. Here we have equal to 0.02x times natural log of e. Okay, so that's the property we're using. So this exponent here goes right in front of this natural log. So we know that natural log of e is equal to just simply 1. So that's exponent is 1 here. The base is e, so that must be equal to 1. Just like we had before, if I had log of 10 is equal to 1. Remember that? Because why? Because exponent is 1, the base is the same as the exponent. So in general, if I have log of b, if the base is the same as exponents, whatever number here exponents is, that's what would be equal to r. So as you see here, since the base are the same, so natural log of e would be equal to 1. Just like that here. Log of b to the power of r is equal to r if the base are the same. Log of 10, remember, was equal to 1 because the exponent is 1, matching the base. So in this case, natural log of e would be equal to simply 1. So on the left hand side, you get 0.02x is equal to natural log of 192. To solve for x, I divide both sides of the equation by 0.02. So I'm going to use my calculator here to obtain this result, 262.875. So the solution is in the brackets. You can write it as 262.875. Solve an exponential equation. We're going to solve 5 to the power of minus x plus 7 is equal to 9. So to do this, to solve for x, you need to take a log of both sides. So I can move these exponents right front of the log so I can solve for them. We call that log of a to the power of x. That's the same as x log of a. So this x right here can be moved right front of the log. That's exactly what we're doing here. Once you take a log of both sides, these exponents here can be moved right front of the log. So now I can distribute. I get minus x log of 5 minus x, that would be, and then 7 log of 5. So now I can distribute this, solving for x. All right, now we have minus x log of 5 plus 7 log of 5 is equal to log of 9. Remember, we're solving for x. The only terms contains x is this term here. I'm going to isolate this. So I'm going to subtract 7 log of x from both sides of the equation. That goes to the other side then. Now the coefficient of x is minus log of 5. If I divide both sides by minus log of 5, this would be my x. To calculate this, we need to use our calculator. We substitute these numbers and use our calculator to solve, and the solution set is 5.635. So general method for solving an exponential equation: take logarithm to the same base on both sides, and then use the power rule of logarithm, or the special property log of b to the power of x would be equal to x if the base is the same as b. There's a special case if both sides can be written as exponentials with the same base. You do that, you do so, and set the exponents equal.